What up? It's time for day 8 of Advent of Code. For part 1, I highlighted the things that we should pay attention to. So we find ourselves on the roof of a top secret Easter Bunny installation, and we take a look at the familiar huge antenna. We find that there are actually many such antennas, and each antenna is tuned to a specific frequency indicated by a single lowercase letter, uppercase letter, or digit. And so here's an example of what our map might look like, where the periods represent empty spaces and the symbols represent antennas with a given frequency. And so they give us the definition of something called an antinode. They say an antinode occurs at any point that is perfectly in line with two antennas of the same frequency, but only when one of the antennas is twice as far away as the other. So for any pair of antennas with the same frequency, there are two antinodes on either side of them. So for example, we have our two antennas of the same frequency here, and then our two antinodes that are twice as far away from one antenna as the other in the same direction, right? So if I take this distance, I duplicate it, I get this antinode. And if I take this distance and I duplicate it, I get this antinode. And so they show us an example of 3 antennas, and we can see all the different pairs form several antinodes, and some of the antinodes are out of bounds, right? And so those don't count. They also tell us antinodes can occur at locations that contain an antenna. So right here, even though there's an antenna with a capital A, because if we take this distance and we duplicate it, we would get a antinode here. This counts as an antinode. So they ask us how many unique locations within the bounds of the map contain an antinode. So now, how do we actually approach this problem? Let's take a look at our input. What we can do is just simulate what we were doing in the examples, right? For each antenna of a certain frequency, we'll look at the distance between the first and the second, and then if we go that same distance further and it's in bounds, we'll count it as an antinode. And one way to make it easier is that instead of thinking about this direction and this exact distance, we can just use a Manhattan distance, right? We can split it into X and Y components. So I'll look at the difference in the X direction and go that much down from the second antenna in the X direction. I'll look at the difference in the Y direction and go that much over in the Y direction, and it'll give us the same result. Let's parse our input. If you look here, I have the input next to my script, and it looks as you would expect. And this one's going to be pretty simple. I'm just going to take I'm going to name it grid, and I'm just going to take each line and make sure I take off the new line for each line in the file. And so if we print this out, we see that we have a bunch of lines representing each line in the file that we can work with pretty easily. So first I'm going to get the dimensions of my grid, and then I'm going to find each antenna with a given frequency and keep track of its position. So to do that, I'm going to make a dictionary called positions, and it's going to hold lists of positions for each antenna with a given frequency. So to do that, I'm going to use a default dict from the collections module. And what that will do is that when I append to it, if the list doesn't exist, it'll initialize with the empty list. So it'll save me some work. So now I'll just iterate through each position in my grid. And if that grid position is empty, so if the grid position is period, then we want to continue, right? Because there's no antenna there. Otherwise, we want to take our positions dictionary, and we want to take our frequency, which we can just represent with the value at the position in the grid, and we want to append our current position, which is I and J. And so now if I were to print positions, we should see that we get a dictionary of positions for each frequency in the grid, right? So let's try this for part 1 of grid. And you see we have a dictionary here that maps 8 to 020, 413, and so on, D to 022. It maps each of the frequencies to their positions in the grid. And so now I can simply count all the antinodes as we described by counting all of the pairs that have an antinode in bounds, right? So one thing we need to be careful of is that it might be the case that two different pairs, so like pretend these have the same frequency and there's an antinode here, and then these have the same frequency and there's an antinode here, they might have the same position. And so if they overlap, we don't want to double count it, right? An antinode just corresponds to a single position. So what I'm going to do is I'm going to keep track of every position that is an antinode and then count the number of those positions that are antinodes only. And so to keep myself from overcounting duplicates, I'll maintain a set and then just return the length of the set at the end, right? So I'll make a set called antinodes, and then I'm going to look at all the positions of the nodes with a given frequency. We don't actually care about the frequency, so we'll just use the dictionary values method to get the values of each key. Once I have all the positions of the antennas with a specific frequency, I'll look at each pair of antennas and see if the corresponding antinode is in bounds. So I'm going to name the first position X1, Y1. And I'm going to name the second position X2, Y2. And if the positions are the same, it doesn't actually correspond to two separate antennas. I'm looking at the same antenna twice, and so I want to skip it, right? Otherwise, to find the difference in the position, I want to look at the difference in the X component and the difference in the Y component. And so to do that, I'll just subtract the X components and I'll subtract the Y components. And then if the second point plus the X component and Y component is in bounds, I'll add it to my antinode set. And then I'll return the length of my antinode set at the end. And so notice we're actually giving each antenna an opportunity to be the first position and the second position. This way I don't have to worry about looking at both sides of each pair. I can just look at one side, but then look at it in both directions. And so I'll make sure I'll count all the antinodes. So if we run this, see we get 394, which was the answer for part 1. For part 2, they tell us that it turns out that an antinode occurs at any grid position exactly in line with at least two antennas of the same frequency, regardless of distance. So this means that some of the new antinodes will actually occur at the position of each antenna. So if we look at an example, it would be like, look at these two zeros. Now these two zeros are actually antinodes themselves because they're in line with themselves. And then also the old antinodes are counted, but then if we keep going, we see that these antinodes are also counted as well. So basically we want to keep looking at distances continuing. And so they ask us now with this new rule, how many unique locations within the bounds of the map contain an antinode? And this actually will require pretty minimal change on our part. We can just take all of our old code, and the difference we can make is that down here, we can make sure that we add the current point to our antinode set. And instead of making this an if, we can just continue to update x2, y2 with the difference and add it to our antinode set until we go out of bounds. Right, so we can just say x2 plus equals dx and y2 plus equals dx, and then we could just append x2, y2 to our set, or I should say add. make sure we're using dy here. And now if we run this, we get our new number, which is 1,277, which is exactly the amount which was for part 2. That was a pretty easy day 8. Thanks for watching. This one was pretty short. If you want to solve LeetCode with me on the daily, come join my Discord. The link's in the description down below. I'll make sure to post my answers on GitHub. And yeah, have a good one.